Okay, so we're going to do a review of data structures, some of the stuff that you've already learned, and then we're going to go and do some more stuff, a little bit of recursion, some tree stuff, and some data notation, which I think for most of you this will be new. Has anyone done anything with like recursion or anything like that before? A little bit? Okay. You've done some stuff? Okay, so I'm not an expert in all of this stuff, but I do know that this is really helpful stuff for you to know, especially for when you're going and doing interviews. If you want to do anything with development, there a lot of times you're going to have questions about, you know, how efficient is this program? Why should you use this structure? So on and so forth. So I just want to really go over, you know, what the different structures are and how you can use them, how you should implement them, stuff like that. Feel free to ask questions. I want to answer your questions and make sure that you guys know what's going on. And I hope you find this helpful and that like the extra stuff that you learned will be good too. Okay, any questions before we start? Cool. Okay, so we're just going to start off with talking about some of the basic structures that we've already looked at. And I'm going to go briefly over these a little bit, but just because you've already learned what an array is both in your intro to program class and in this one, and that's one that you're going to use a lot. But arrays are contiguous data structures, which means that in memory, all of the elements are right next to each other as far as the memory addresses. So they're right next to each other, which makes it really easy to go and search through it because you don't have to go and look anywhere else. You just sort of like, oh, who's your neighbor? And go and find them really fast. They're fast and simple, and they are also a huge interview question. I think, has anyone used HackerRank? Okay, HackerRank is like a really good way to prep for programming interview questions. If you go on there, they have like an interview prep kit thing, and it says that 70% of interviewers use arrays as a question for interviews. So knowing how to manipulate an array in the language that you want to use is really important. There's different things like doing an array reversal, so you reverse all the elements in an array without using some built-in function. You know, how would you do that? Things like that. We're not going to go over that here. Those are questions that they actually have. Like you can go program them out, and they'll run test cases to see how well you do it on things like HackerRank or LeetCode. But it's really important to know what arrays are. They're like one of those basic data structures. Any questions on arrays? Okay. Array list. Who's come from CS142? Okay, so those with CS142 background, you've used vectors in C++. They're basically the same thing. And so they're unstructured. And they're flexible. So what we mean by that is like the unstructured part is the data type. They don't care what data goes into it. You can put strings, you can put ints, you can put dictionaries, you can put queues, you can put whatever you want inside of your array list, and it just doesn't care. It's also flexible because it will grow depending on how many items you're adding to it. The only thing is they're contiguous, and so if you first create an array list, it'll set up space for it, and then if what you are adding exceeds the amount of space that's given, it will double in size and still be contiguous, but it will double in size, which is also inefficient because if you're not using up all that room, then that's just space that's allotted for this array list that isn't being used. So in that sense, like it's great that they're flexible and that you can expand them and not have to know exactly how many elements are going to be in it. However, they're also not the most efficient. Another problem in C# is that because you can add multiple data types in, when you're getting things out from the array list, you have to be cognizant of, is this a string, is this an int, and checking for that before you start using it, depending on what functionality you want. So array lists, unstructured and flexible, but they do have some disadvantages, especially if you're working with very structured data. Okay, questions? So let's talk about linked list and double linked list. So in C#, has anyone taken CS335? Okay, it's over here. So you'll be like, wait, is there anyone else? Okay, if I say anything wrong, you guys can probably say something. So in C# we have list and we have linked list. What I think is kind of dumb about that is the implementation of them. The list is a linked list and the linked list is a double linked list. Makes it a little confusing, but that's just their naming schema. So linked list is made up of a bunch of nodes. Each of these, where you have your data and then your next, this whole thing is a node. So the data is whatever, when you're creating a list, you have to specify the data type, string, int, whatever. That's what's actually getting put as the data of the node. And the next part is a pointer to the next node in the list. So what's nice about linked lists is that they're not contiguous. This means that I can have the first node be right here in my memory, like that, and then I don't have to allocate more memory that's right next to it for the next elements that I add to the list. So maybe the first one's here, but then the second one ends up being over here in memory. Okay, and so that first node is going to have a pointer that says, hey, the next node in the list, point it at this location in memory, and that's where you're going to find the next node. So that's what these pointers are. They're just saying, hey, here's where the next node is located. We have a head node that's just pointing to the first element in your list, and the last element of your list will be null. Okay. So what's nice about this is they're flexible and they're structured. So you have the flexibility because it can grow as long as you have memory, and but they're structured because you have to specify the data type. They are one directional. So if I'm this node here, the second one in the list, I don't know where I came from. I can see where I'm going to go and like where the next element is in the list, but I don't know what where the first one is. And so when you have to iterate to be able to search for a particular element in your list, you have to go through every single one up until that. So say I'm looking for the element that has the value of C. I have to start at the beginning and say, okay, you're not A, you're not C, where's the next one? Go to B. B, you're not C, where's the next one? Find it. Oh, you're C, this is the element I'm looking for. So that is one kind of disadvantage of it, is that you have to iterate through all the elements that precede it to find what you're looking for.
How does a double linked list have slower iteration?
I'm not totally sure about that one. I kind of copied some notes from the data structures stuff that the document that Dr. Anderson has out there on GitHub. Let me talk about double linked lists and then I'll try and address that. But I'm not totally sure, so I might get back to you later, okay?
Oh, okay.
But with a double linked list, it's basically the same as a normal linked list, except for now you have something that points to where they came to the previous node, and you have something that points to the node that's next. So this way you can go back and forth. So it's going to be a little bit faster for iteration deletion and more efficient organization. For slower iteration, I can't think of a good explanation right off the top of my head. So maybe I'll look something up and get back to you. However, what's like something like a double linked list could be really good for if you have like undo or redo functionality in a program, because you want to know in that kind of situation, you want to know, okay, what happened before this point and what happened after this point, and so you can keep going back and forth. You could also implement undo and redo probably with like stacks and queues, but this is also another good use case for something like this. And something that I really want to emphasize is that different data structures are going to be great for different use cases. The idea isn't use the same data structure for everything. It's like, okay, this is a scenario, which one is going to be most applicable, which one's going to be most efficient for what I need. And if I don't need a certain functionality, I probably don't need the data structure that's associated with that functionality. So yeah, linked list, double linked list. Any questions? Cool. Okay, so stacks. We've already learned a bunch about them, but they're LIFO, so they're last in, first out. I thought it would be really good, actually, to show you kind of, here's an implementation of C#, and then here's one of JavaScript. Just because it's great to know C#, but there's always good reasons. Like, it's really good to see how other programming languages might do the same thing. I mean, like, in the past week, I think I've used C#, C++, Python, and JavaScript all within the past week doing different stuff. So, like, knowing how they work in different languages is really helpful. Anyway, with a stack, it's like the plate example at a buffet, where you can only take the thing that's on top, but once you take it off, then the next thing kind of like keeps going. It keeps pushing it up until the stack is empty. So here we're kind of doing the same thing where we're pushing to our stack. We can peek, which just means look, return the value of whatever's on top. Pop will return the value of whatever on top, but it will also remove it from the stack. Contains, we can easily check and see what the value, if the stack contains it, but my guess is in the implementation of contains in the background, it has to do some sort of for loop to go through every single item in the stack and see if it exists in there. So, I mean, you can check it, but that also might not be the most efficient thing. You can clear a stack, and then you can get the count. What I think is interesting about the count is, if you notice, we're not calling a function called count. We're just calling count. Does anyone kind of have any ideas of what that might mean? Kind of fishing here, but
would it be like an attribute that counts the elements?
Yeah. So it counts the elements, but how do we maintain the count? You know. So what's probably happening is every time we push, as part of our push function, we're going to say the count, we increment the count. Every time we pop, we decrement the count. This way, if we have a stack of like 10,000 items, it doesn't have to go through and like actually count how many are there. We've been taking care of that every time we push and pop because we're controlling exactly when things get added or when things get removed. And so then we just have a property that it's going to be way more efficient to have that property as our count rather than doing some sort of for loop to go through all of the elements in there. So this is something I think that's a really cool example of how you can implement a property rather than having some method that's going to be more inefficient. Did you have a question?
I was just going to ask kind of how would you format that? Because it wouldn't be just count and were you saying you have to set up like the counter for it?
So there's a class somewhere out there that's called stack, right? And that's what we've been using. You've been creating objects from that class that's already implemented. And in there, they probably have a attribute for the class called count. And then every time the pop, or every time the push method, it just increments the count, that attribute. Does that make sense?
Yeah.
And then pop, it decrements it. Okay.
On the JavaScript one, how is that different from just an array?
So that's the thing. This is what I think is interesting is JavaScript does not have an implementation for a stack or a queue actually.
Okay, so you could still, on a stack with JavaScript, you could still say my stack index of 3 and look at what's in the middle.
Yeah. So I think what's really interesting, JavaScript's funky. I mean, I love it, but it's really funky because of how it's all implemented. But if I'm trying to operate under assumption that my array is a stack, I'm going to do the functions or use the functions that would allow it to operate as a stack. Does that make sense? I probably wouldn't cut corners and say like, oh, now it's a queue and not a stack. I'm like, no, I need my I need my data structured like a stack, and so that's how I'm going to use the array. If I need it structured as a queue, that's how I use it. There's also something called decks, which are basically stacks and queues combined, and so they kind of go both ways. But like, I'm glad you brought that up, because in Java, in some languages, they might not have an implementation, but they do have things or structures that you can use as a stack or as a queue.
Okay, one more thing. So in C#, you couldn't just look at one in the middle, right? That's like a real stack.
Yeah. So this one is going to be like, you have to pop everything off just to get to that one. So with your assignments that you guys have due, I think on Monday, when it says like delete from, if you're going and you're finding like, oh, here's the thing to delete, maybe what you could do is pop everything off into a different stack, find that thing, find that element that you need to remove, get rid of it, and then push everything from that temporary stack back on top. And then so you still maintain that original stack and the structure, but you can remove a particular element. And what you'll see is that when you do that, it's actually slower than if you just move things. And I'll show a little example of that later.
So are these like specifically C# or are they just general data structures?
These are general data structures. It's just each, and most of the time programming languages will have similar implementations, but it is important to recognize that some of them are going to be funky and they might not do it the exact same way. And you can, if you take CS235, you create your own of like all of these, right? Basically that. So like that's basically what we did that whole class, is just, okay, here's what a stack does, now go create it. Okay. Really quickly, queues, they're pretty much the same thing. It's just instead of starting at the, or like stacking on top, it's FIFO, so it's going to be first in, first out. And I think that the example of a print queue is really good. Like, it has queue in the name, but it's really good example of like in your applications where like the first job that gets into the print queue will be the first one that gets printed out. Yeah, I mean the only basic differences are the enqueue and the deck. Or DQ, sorry, not deck. DQ methods for a queue versus a stack. Now really quick, any questions on queues? I don't want to go over them too much. I've already been over them. Okay.
Can you use the delete from like the same method that you put it out and then delete one and then put it back?
Yeah, that's what I would probably do with a queue. Yeah. Just stick them in a temporary structure, and then delete the one that you need to. Or actually, with a queue, I just thought of this. You could probably move them all into a new one, depending on how long it is, you know. And rather than if it's like shorter, for just to move the rest of whatever you have from your original one to the new one, then do that. Don't worry about it. Anyway, let's keep going here. Let's just talk about dictionaries really quick. Dictionaries, I would just like to think of them as key value pairs. That's the best way to think of them. Sometimes programming languages will call them maps. And JavaScript actually has a map one, but everyone just uses normal JavaScript objects. And part of the reason I'm adding the JavaScript in is because, like, if you're going to do web development, yeah, maybe you'll use C#, Python, whatever you want, but like you'll always need to use JavaScript. So, like, if you're doing web stuff. So that's where I also have that as an example. Dictionaries, you can check if the dictionary contains a particular key or a particular value. You can remove based on the key. I think you guys have been seeing this already. And then you can do similar operations in JavaScript, Python, whatever other language you want to use. Any questions about dictionaries? I think they're not too. We've covered them quite a bit in class, but are we good there then? Thumbs up? Yeah? Okay. So which one should you use? This is a hard question because it kind of depends. But can I get like 5 volunteers? Okay, so just come on up. Whoever comes up, we get 5. Then, okay, perfect. So I'm going to have you guys be a stack. So I'm going to start with you. I'm going to push you onto the stack. Yeah, just push. Okay, you get pushed on. Now you get pushed on. You get pushed on. Pushed on. Okay, so we have in this, our stack would have a count of 5. And we're going to, if we're looking at a, just say that all of you guys have, your value is just a number, 0 based, like, pretty much like an array. But if we wanted to get, whoever's number 3, so you're 0, 1, 2, 3, then how do I do this? I'm going to have to pop, 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 and then I finally get to my value. So I have to do 1, 2, 3 different steps in order to get to this. Sorry, what's your name? Eric. So it took that time to get to Eric. So go ahead and go back in the line that you were. Now pretend that you guys were like an array or something like that, okay? And if I say I want my array element 2, then whoever says that, yep, you come forward. I don't have to look through anyone else. You immediately come forward. This is the same thing that happens with a dictionary. If I say, hey, if I have my dictionary, and sorry, I don't know all your guys' names, but I said your name, then you could immediately come forward and tell me whatever value, like your last name or something like that. You could immediately come forward. I don't have to go through everyone else in the list up until you. And so there's scenarios where you're going to need something like a stack, where it's ordered the way that you need it to be, kind of like those callback functions that Dr. Andrews has talked about. But there are other times where I just need to pull the information directly, and it's indexed, and I don't need to go through everyone else. Okay. Thanks, guys. You can sit down. But does that make sense conceptually, how there are different scenarios where I need different types of structures? And so it's the worst answer, but it depends for which one should you use.
So you're saying with dictionaries, it's like you call the position number 3, and then they just return like their value.
Yeah.
Basically.
Yeah. So.
But don't they have like 2 values because you have your like key?
So you'll call the key, and it will return the value. Does that make sense?
How do you call?
So. Yeah, let me just pull over here. So like, say I have a dictionary called, I'm just gonna make something up, like, dictionary equals, like, Peter Garrow, okay? So if I wanted to, if I wanted to get the value of whatever is at Peter, then I can say dictionary Peter, and like if I was in the right line. So I could do something like this, and it won't return Peter, it will return Garrow, because that's the value at Peter. So it's very similar. You can do it, you can get whatever values at that key very similarly to the way that you'd get a value at a certain position in an array. So if this was an array instead, like Peter Garrow, then if I said like console right line array of 1, that will also return Garrow. But do you see how these they're obviously different, but they, as far as how we're actually getting the data, it looks very similar. And so you can just kind of think of it that way.
So, like, the only reason you would use, like, a stack or a...
Queue?
Queue, yeah. Would that just be if you wanted to, like, maintain the order?
Yeah.
The elements?
I think if you need to maintain order, then definitely using something like a stack or a queue. You could even use a list or like, it's really going to depend. And sometimes you'll have cases where you're like, oh, I can use an array for this, and you start doing it, and you're like, I can't use an array for this. Let me go change what my structure looks like. So you don't need to know right away, but like, and as you go, something might come up and you're like, oh, I actually need this functionality, I need this. So maybe you implement something yourself, and that's fine too.
There's some sort of like issue example where you want to keep it programming.
Yeah.
Like,
Oh, give an example.
yeah,
So, like, I mean, using queues is pretty interesting. Who's ever gone to the IS-201 lab and like gotten help there? And so when you sign up, and then they have like the list of everyone that's signed up, right? And they go from the top of the list down. Now, if I said, oh, this is actually going to be like a set or something like that, sets are another structure that they're an unordered list of things that they don't have duplicate values. Like, oh, I don't want duplicate values in my list for who I'm going to go help. But the problem is that's also unordered, so I can't tell who came in first to get help. So I could end up going and helping someone that had been there for like 2 minutes for someone that's been waiting for an hour. So that's somewhere where I would definitely say use something more like a queue in order to structure that. Yeah. And I can't think of a stack right now other than like the function callbacks. But yeah.
So is there a restriction of like what kind of data I can put in each of these? Like, can you put objects in all of them if you wanted to?
Yep. So you can, so like say that you needed for your stack, you actually needed like a student object, right? Because you had a person class that you can make student classes, that you extend to make student classes, and then that student class you make a whole bunch of objects. You could make a stack that has each element is just a student object.
So with the console.write-line, is that just like you put that in your queue and then it'll just like display it?
This would just be console. This would be in probably my controller, because my console. Because my console.writeline is just like the little dialog box that comes up in C#. This wouldn't be how you print to a web page. That would be like in a p tag or something like that.
Okay, so where would
So like if I had my HTML, then like, and I think it would be like @viewBag. I don't remember if it's capital or not. And then whatever I give my dictionary value name to as, so like dictionary, and then I could do Keter. Does that make sense? So I would just stick that right in there and it should show up. Sorry, this also isn't like, I don't have Visual Studio open, but I figure this is really nothing. Okay. Any other questions? These are good questions, by the way, so. Okay. Okay, I think we're going to move on from data structures for now. There's more out there. I talked about sets briefly. I don't think that we should go through every single thing right now. But I wanted to give you some more exposure to, like, yeah, you learned about these. These are really important, and like interviewers do ask about this stuff. But so I want to move on to some new stuff that most of you probably haven't learned about, unless anyone has any questions. But okay, so we're gonna move on. So who's heard about recursion before, other than my 235 people? Okay. So recursion it's basically a method calling itself over and over until a condition is met. Up until now, you probably haven't really dealt with too much recursion stuff. You've dealt more with loops in an iterative cycle. So this is where a loop executes a block of code repeatedly until a condition is fulfilled. So this condition would be like, oh, I receive some number n, and I keep going through a for loop until I have reached n, right? And I keep executing inside the for loop. Recursion happens when I'm a function, and and inside of the function, it calls itself. So we're going to see that in a second, and we're going to use a factorial example for how to do that. So factorial is when, so like if you have 5 factorial, it's 5 times 4 times 3 times 2 times 1. Okay, it's just whatever you have all the way down, whatever number you're given all the way down to 1. So if we look at this iterative example, we go through this, we get the number, we're just going to set some int result equal to number, so that would be like, if it's 5, then this will equal 5. 5 is the number minus 1, so now I is 4. We're going to go down until I is 0. So it's going to be result times 4, 5 times 4, and then that times 3, that times 2, that times 1. Right? And then we're going to be able to return result. So it comes out to 120. Over here, what's happening is we say we have what we called like an exit condition or an exit clause, where we say if number is equal to 1, return 1. We're saying this is the last thing that we're expecting here, and so this is kind of our, hey, you're done looping or like calling this method over and over again. If the number is not equal to 1, we return number times factorial recursion number minus 1. So what's going to happen here is we get, if we start with 5, actually, I'm going to draw this out. It's kind of complex, but I think that seeing will help. So at the beginning, we're going to have our number, I'm just going to say n equals 5, right? And this is our first iteration through this method when it comes in. This is going to return n1 times, and then we're going to say that it's going to be whatever, like this, our second method returns, our second method call returns. So here we're going to put, let's just put n2, okay? n2 is representing the second iteration of, or not second iteration, second time that this method is called. And I know this is going to be confusing while I'm writing this out, but I think that we can like get it back together at the end. So n2 is going to equal 4. We see that because we have number minus 1. So that's n1 minus 1 here. So that's going to be our n2. This is going to return n2 times n3. n3 equals 3. This is going to return whatever we get from our fourth iteration. N4 equals 2. N4 times N5. And then finally we get to N5 equals 1. Okay. So hopefully you can see that we started with 5 as the number coming in, and then we keep calling this function over and over again, but we keep decrementing whatever number first came in by 1 until we're getting back all the way to 1 here. So now that n is 1, we know that this is going to return 1. So n5 equals the return value of whatever it had, so this is 1. N4 we had equals 2, right? 2 times 1, it stays at 2 just because of the 1. But now we take this value and we stick it in here. N4 is 2. We said N3 was 3. 2 times 3 is 6. So that's what we're going to put up in the function that had called it before. And we keep working our way all the way back up. Until we get to 120. I know that's not like the simplest thing ever, and it's kind of hard to diagram out here. But what's important to note is that we, in our recursive function, we have an end clause or an end condition, and then we have something that's going to continually repeat or continually call itself. As it call until the end condition is met, it's going to keep calling itself, but then it's going to kind of work its way back up the call stack. Does that make sense?
So what part of the code makes it call itself?
It's
There's
right.
no, like, for loop or anything like that.
It's right here where it's actually calling its own function. So if we see here, it's factorial recursion. Here, it's calling factorial recursion. So kind of like that stack, the callback stack that we talked about earlier. It's saying, hey, we're going to do, I'm just going to call it fr of 5, and then we're going to do fr of 4, fr of 3, and so on. So once this one's finished, then it can complete whatever happened in this one. Once this one's finished, it can complete the rest of this one. This is kind of a good example of how that stack is really useful.
So I understand how it like calls itself and keeps going back, but I don't understand like how it works its way back up, I guess.
So if I call a function, so if you call a function and just in a normal, not recursive, I wait for that function to complete and then I continue on with the rest of what I'm doing, right? So here it's waiting for the result of factorial recursion number -1 before it returns this. So it gets all the way down to when n equals 1 and it says, oh, return 1. So this goes back up. This return 1 is the result of when number -1 equals 1. So it's 1 times whatever the number was before that. Here that would be 2. And so then this iteration of the function then returns 2 times 1. So then this becomes for the next one up, or sorry, next one down the stack. Does that make sense? It's hard to wrap your mind around.
So this wouldn't actually return the value you're looking for by the equation, right? Because there's return on 1. We have to save that. Does that make sense? Like we get this code, we have to save the number that is multiplying each time.
It would return both, wouldn't it?
Huh?
Because it returns the 1 as it's like going down to the bottom. It gets to the 1 and it says like, we've reached the point, and it says execute the one that was like, you know,
Right
like,
before
return
it,
1,
yeah.
So
So it returned 1. And so all we're doing is we keep returning whatever the number that was passed into it
Right.
times whatever the result of this function is. Eventually it's just going to be return 1. Once this is executed, we don't execute any more of the code, right? Because we returned a value in the function. So it's 1 times 2, that equals 2. And then the next function that was called before that becomes 2 times 3, that becomes 6. 6 gets passed into this one, 6 times 4. And then 24 times 5, and that was the first function call. So we've gone all the way down our stack, and that's what we're returning from fr5. Does that make sense?
Kind of. Because in the end, we're just returning 1, right? I get the recursive part, and then at the end of it, aren't we just returning
We're returning,
1 out of the function? Or
you're returning the very last, the last function. Let's go all the way up. fr. Okay, does this kind of make sense how it's a stack?
yeah.
So this one, we're returning 1.
Okay.
Right? This one, we're returning 2 times whatever the thing on top of it, or this function will return, right? So that's going to be 2. This one then is going to be our 3 times 2, so 6. This one returns 4 times 6, 24, all the way to 120. And since this is the last one, this is what ends up showing up.
Okay.
So if we called this from some other function, then and like got the return value, then like we'd end up with 120. Does that make sense? There's different implementations of like there's different ways to do recursive stuff. This isn't just the only way or the only example, but
Do you still see all those other ones, 1, 2, 6, 24?
no, unless you were like printing out somewhere. You'd probably only see this one because I imagine if you wanted to get a factorial of something, you'd have that as part of a different function. Say, hey, I need the factorial of this. return it. It's not going to return all of these. It's just going to return the first one to that other function. I know this is new because like we haven't really talked about this.
So I'm still a little bit confused about what's causing it to keep going through the process and loop. Is it just because it's the if the number equals 1, and if it's not that, then it just keeps going until it reaches that?
Yeah, so the if number equals 1 is like the exit clause that says, hey, we're not like in this return it's not calling itself, right? So if it's not 1, we're going to continue to call the function. Yeah. And these are kind of like each of their own instance of the function call. Okay.
I don't know if this helps, but I think of it kind of as like movie Inception.
Yeah.
Like,
I was bringing that
go
up.
deeper and deeper and deeper into dreams, and then once they get to like the lowest dream is when like they have to change something and something happens, and then they go back up. So you're returning whatever's in this level to this level, and then you return from that level to the next level, and then you return all the way to the
Yeah. I think that's a great example. Yeah. And for those who have known about recursion, that makes sense, right? Like what we talked about. Okay. So now my question for you guys is, which do you think is more efficient, the iterative one or the recursive one? Okay. So my argument here, wait, who says recursive? Raise your hand. Okay, who says iterative? Okay. My argument here would actually probably be the iterative one. And my reasoning behind that is because with recursive functions, you also end up with this overhead of calling functions, which is going to take up like some amount of time. And I mean, it's so minuscule that who really cares? But with this, it's just doing a loop and it's just looping through it all in one function. You don't have this overhead of adding it to the stack and then like having to do all of that process. So in this case, it might be better just to make some iterative function. But in other cases, recursive is going to be a lot more efficient, especially if you don't know if there are conditions that need to be met that aren't just like counting down a number or counting up. Okay.
What would an example of that be?
Where recursive would be better?
Yeah.
We're going to talk about trees in a minute, and that is inserting and searching in a tree is great.
This is kind of like an interview question, but I know when I took CS235, it talks about big O.
We're going to talk about some of that.
Okay, did they ask us that in the interview? I guess if you get to it.
Yeah, I think that they ask it, but they're like sneaky about it. They're like, how efficient is this? Instead of saying, what's the big O? You know, some might say that, but they'll ask about efficiency and complexity. Okay, I'm gonna move on. Sorry, I need something to drink. Really quickly, here's some of the key differences. And we've kind of talked about these, so I'm gonna, we've already kind of talked about some of this. A conditional statement decides the termination of recursion, while a control variable's value decides the termination of the iteration statement. What that's just saying is that over here, we have an exit clause that like once that's met, then we're like, oh, we don't need to keep doing this recursion and we're going to come back out of it. Here, we're just waiting for this condition to be met or like to not happen actually. It is independent of what is getting passed through the methods. So that's why it's kind of that control variable. Infinite recursion. So if you don't make your exit clause, if you structure it poorly and there's some condition where it doesn't meet, you could have like an infinite loop basically. Infinite recursion is going to lead more to a system crash, but infinite iteration consumes CPU cycles. I don't really know about all of that, like what's happening with that, but just know that can happen. Like I said before, recursion has more overhead, and so because it has to keep calling functions, whereas you don't have to do that with iteration. So that's kind of something to note of, and recursion makes code smaller while iteration makes it longer. So if you notice here, there's actually less code written here than over here in the iterative side. That doesn't necessarily mean that it's faster, but it does mean that there's less to look at. And sometimes programmers like to have functions and things that just less lines of code. Okay, any other questions about recursion? Okay, it's new. I don't expect you guys to like be experts in this right now, but I think the exposure is helpful, and if they ask something on interview, you can at least say something about recursion and like what it means. I'm kind of looking to you guys for, now that you've been exposed, you guys can go and become the experts in this, because that's what we do. Let's talk about some trees. So we're gonna cover like what the basics of a tree data structure are, what the basics are, what a binary tree is, and then what a binary search tree is. And it's kind of going to build off each other. So this is a very, it's a basic just overview of what a tree looks like. And trees are a little funky because they're a little bit more conceptual than our other data structures. With trees, not every programming language is going to have an implementation of a tree. That means that they're not necessarily going to have a class, like a class tree. We have, in C#, we have class for Q and for def and everything. That's not necessarily the case for trees in all languages. And so you can implement your own, or I'll show you how there are ways where you can actually use things like a sorted array to implement the concept of what a binary search tree is. Anyway, with trees, like we talked about before, we have nodes in linked lists. We have nodes in trees as well. Each of these circles is a node. So the node has a value, it has data, and then usually it's going to have a point, it's like going to be pointing at its child nodes if it has it. So like here, A has a child node B, and A also has a child node C, and it's just pointing to where those are. We would call, like D has children, and so we'd call D a parent node. You can also look and see that there's a subtree right here. This is, if we could cover all that up, this could be its own tree. Does that make sense? Where it still keeps that same general structure. So we call these subtrees. Basically, every node can be its own subtree because a node can have it could have 0 children. Leaf nodes are what we call when they don't have any children. So they're just kind of like the leaves on the tree. The connection between, and you guys don't need to have all this stuff memorized. I just want to give a brief overview. The connection between two nodes is called an edge. Okay, and here's the definition. So like I said, you can come and look at all this stuff on in the deck. Another thing is the height is the length of the longest path to the leaf. So in our example, if we wanted to see what the height of this was, we could go A, B, E, J. That's the longest path. There are other ones that are the same length of 3, but that's how long the path is. And so we would say that this tree has a height of 3. But then its depth is the length of the path to its root. So that just means that, is this, like G is at level 2, so its depth is at 2, level 2 there. Okay. Let's open up some visualizations and kind of see how this works. So here we're just going to make this is a random binary search tree. And we're going to start inserting stuff. And this is a great example of how recursion could work with how they insert things. Really quickly, a binary search tree, you'll see here that we have 54, and then on its left, we have 48. So, and then on its right, we have 75. Everything in a binary search tree, every node to its left needs to be less than that node's value, and everything to its right would be more or greater than that node's value. So we can see here, everything on this side of the tree is going to be less than 54. Everything on this side of the tree is going to be greater than 54. So now if we want to put in like, What should we insert? Let's do what? 37. Okay. So if we insert this, it starts at the root. It says, oh, 37 is less than 54. It's less than 48. It's greater than 33. It's less than 38. So it ends up where it's supposed to be. And now it's doing that recursively. It's a function that keeps saying, hey, it's going to look something like, I'm going to insert this, check the node, check its left child, and check that node and see if the value that I'm trying to put in is greater than or less than it. If it's less than it, do the same thing, but stick it in, have its root be like the left node. And I have another visualization that will help with that, showing that. So let's try and like find a value, say like 70 here. It does the same thing where it's using recursion to go and find where 70 is. Let's just insert something else in here. So if we say like 71, now it's going to go to the other side of the tree and insert it there. Okay. There's one other visualization that I think is actually pretty cool because it shows like what the pseudocode would look like to make it happen. Okay. So let's go ahead and put these in. Let me open these. So it's going to put in, first it's going to put in 1, and then it's going to put in 77. So it says over here, this is like the pseudocode for what's actually happening. It's checking if the insertion point is found. If it is, create the new vertex, or the new node. If the value to be inserted is less than whatever it is, then go to the left. Go to the left child. If it's not, go to the right child. And do all of this again, over and over and over again. And so it's just calling itself until that's been completed, and then it says, hey, I'm done. If we want to remove, so say we remove, let's do 76. So it's going to do the same kind of traversal. It starts at the root, and then it's going to go and change this thing. What's interesting about with a binary search tree is, I don't know if you saw it there, it got rid of the 76, and then it made 77 take its place, but then we don't want to leave 61 out. 61 also still needed a parent, or it needed to be attached, and so it moved 77 to having a child node of 61, and then could remove everything. There. Again, this isn't something that you need for this class, but I think that learning a little bit about trees and seeing how they work is really useful, especially like I've had a bunch of questions about trees in interviews and stuff. Yeah. Okay, I'm gonna keep going right now, but can you guys see how these recursive functions are really useful in this kind of scenario where it doesn't know how many nodes it has to go down the tree in order to put it in the right place, but you need to keep doing the same thing over and over again.
Okay. If you could just describe some of the use cases for search trees.
I'm going to get there in just a minute. Is that okay?
So this is what, when we talk about like complexity of a function, is this what they're talking about, like how many times you have to go?
Not yet. A little bit longer. Another thing really quick with trees, Eric, great. Sorry, I just thought of something really quick. Trees are also like, one of the best ways that we can think about it is like a family tree. And it's those relations between them. So like you could say, oh, you started at your great-great-great-great-great-great-grandparent or whatever, and then you're like, okay, how far down, like what's the longest path to you right now? Or something like that, you know? And like that's just like a practical example. I'm going to show how you might use it conceptually with a sorted array in a little bit.
So binary tree is a data type, right?
Not always. As I was saying before, that like a lot of it is more conceptual how it works. Not every programming language has like a binary tree data type, but you can create your own and like put stuff into it, or you can. I'll show you like with a binary search tree, you can implement it as a sorted array. So we can implement the concept of it into an array, something that we already know. Does that make sense? You'll see in a second as we get to it. Okay, binary tree, like I said, a node is going to have a left and a right value, or left and right child. Binary trees do not have to be sorted. If they're sorted, then it's going to become a binary search tree. A full binary tree, really quick, every node has either 0 or 2 children. So like F would make this not, E would make this tree not full because it only has 1 child. It's either 0 or no children to make it full. Or 0 or 2 children to make it full. And a balanced is just making it as the height as short as possible. That's basically what that's saying there. Let's move on to, searching a tree. I have 2 videos, or 2 little animations here that's going to kind of show the different ways that you could search it. So here, a breadth first is you start up at the top, and then you're going on each level and trying to find the value that you're looking for. So if we look here, as it goes through again, this, how many steps it's taking. Basically, like, we can think about how long it's taking. It says that this one takes 14 steps to find n using this breadth first example. Using depth first, where they go down all the way on one side and keep like looking down. This time it only takes 12 to find it. So there are cases where like different kind of searching is going to be more efficient within your tree. Not all searching algorithms are created equal. But these are 2 really quick examples of just how you could search a tree. Binary search tree, talked a little bit about this. It's sometimes called ordered or sorted binary trees, and it keeps the values in a sorted order so that lookup and other operations can use the principle of binary search. What's really important about this is that what is right in here, where a binary search tree node is larger than the value of its offspring of its left child, but smaller than the value of the offspring of its right child. So that's where I was talking about with one of those visualizations, how it chose to go left because like whatever it was, 37 was less than 54, and 71 was greater than 74, so it chose to go right. So here's a really good example of how it chooses which way to go when inserting into a binary search tree. And this would all be recursive as it gets put in. Okay. Okay. So let's just talk about this really quick. Say you had a sorted array of 10,000 numbers that range from 0 to 100,000. What's the most efficient method to get an index of a given number x? Does anyone have any ideas on how we could do this?
So you probably have a search tree, binary search tree. 500 or.
So you have a sorted array.
Oh.
So you have a sorted array of 10,000 numbers. And the numbers can range from 0 to 100,000. So it's not like these numbers are 0 to 10,000. They could be like a whole bunch. So how would you find any value x? A little bit fishing for this. But so the first way that I think of is if we do it iteratively, if it's an array, I can just go for whatever an array, like for each thing, for each element, just go through, does that equal x, right? The problem is that what if it's the 9,000th element? You had to go through like 8,999 other elements just to find where x was, right? So another method that you could do is you could start splitting up your array in half. So you look at the 5,000th element first. Since it's sorted, you know that if x is greater than that 5,000th element, that it's going to be something on the upper half. If it's less, then it's going to be something on the lower half. So then you can split that half in half. And that's where the concept of a binary search tree comes in binary search. But we're actually implementing it by using a sorted array. And so that's kind of where you could use something like this, where like the idea is there, but you're not actually You don't actually have to go out and build the whole thing. Does that make sense? So here's a really good comparison. Down here, this is the sorted array, and this is like the iterative example, where they're looking for number 27, and if they had to iterate through everything, they would have to go, and it would take 10 steps to get there. It'll show. Versus if you were using a binary search tree, or the concept of it at least, you're basically splitting this in half over and over again. So it's kind of like you'd be splitting however much this is, you're getting the half of that, and then half of that until you finally find it. And that's exactly what a binary search tree is doing. But like, this is just how you don't have to necessarily have the tree. You can also move things from a tree to an array, and you can also move a sorted array and then move it back. So this is from a tree degrading to a sorted array, and this is a sorted array becoming a binary search tree.
So are binary trees like always gonna be like sorted that way, or are there other ways to like?
There's a bunch of different trees. So this is not the only thing that you can do. This is one that I've seen that has been really useful to know about right now, and I think that's a great like start into it. This is not comprehensive by any means, though. So there you can have a lot of different implementations of what a tree looks like. Is that okay? So once again, sorry it's kind of quick to just go over trees, but I think that this should be a good foundation for you to start on to like learn more. And like when you go to an interview, at least you can say something about a tree. Like, oh, I don't know necessarily how to implement this, but this is what I've learned about it, and here might be something that I start doing. Okay.
Can I ask one more question?
Yeah.
So just out of curiosity, I mean, when you're on your PC searching through your files and you type in the search bar for like some document, are they using a binary tree or a sorted array?
I think that they're going to be using a tree because it's way faster to eliminate like half of the results. That's basically what's happening, right? Is you eliminate half, you eliminate half, you eliminate half until you find it. And that's going to be way faster on average than if you just iterate through everything. Now, I've been talking about a little bit about complexity, efficiency, and things like this. Like how long does it take? That's what we're going to talk about with Big O notation right now. So Big O notation, I found a video. He sums it up really well in like 5 minutes, and so I think, yeah, we'll probably end right on time. But this guy talks about Big O notation and about a little bit about efficiency, and yeah, this is something that when you're interviewing and stuff, they might ask, you wrote this function, but how efficient is it, or how long does it take? And this is and you want to say, oh, this has a big O of n or n squared. So if it's n squared, it's probably not very efficient. And they'll say, oh, so how can you make it more efficient? And then you got to think through, what can I change in my algorithm to make it better?
Today we're going to learn about Big O notation. So what is it? Big O notation is simplified analysis of an algorithm's efficiency. We cover a lot of algorithms on this channel, and we need a way to compare them and some idea to take to run. Big O gives us an algorithm's complexity in terms of the input size, n. It gives us a way to abstract the efficiency of our algorithms, or code, from the machines they run on. We don't care about the stats of the machine, rather we examine the basic computer steps of the code. We can use Big O to analyze both time and space. There are a couple ways to look at an algorithm's efficiency. In worst case, best case, and average case. When we're talking Big O notation, we typically look at worst case. This isn't to say the others are unimportant, however. Talk about a few rules. First, Big O notation ignores constants. For example, if you have a function that is a run 5n that runs on the order of Big O of n, this is because as n gets large, the 5 no longer matters. In the same way, as n grows, certain terms dominate others. Here's a list, but I'll show you a visual on the next page.
So
We ignore a drop low.
So really quick, this is kind of really important. This is like saying the big O of 1 is more efficient than big O of log n than the big O of n, and so on and so forth. And so your goal should be to try and, I mean, like, not your goal necessarily, but like you usually want to try and make your algorithm as efficient more on this side as possible. And what he was saying with like they dominate others, it's just these ones are growing at so much that they're at such a greater pace, like exponentially, that it's going to dominate anything else that's in there as part of your big O function.
Order terms when they're dominant.
This is really mathematical rather than like the stuff that we're used to doing in IS. So
And study this chart. It can be found on bigocheatsheet.com, along with a handy guide on the big O of various important algorithms.
and I have a link to this.
Let's run a few examples so you can see what I mean by basic computer steps. We'll start with constant time. Imagine we had the following line.
I don't know why.
This basic computer statement computes x, and notice it does not depend on the input size in any way. We say this is big O of 1, or constant time. What happens when we have a sequence of statements? Notice that all these are constant time. How do we compute big O for this block of code? We simply add each of their times, and we get 3 multiplied by big O of 1. But remember, we drop constants, so it's still big O of 1. Let's look at linear time. Suppose we have the following for loop that prints the numbers 0 to n. We know the print statement is big O of 1. This means the block of code is big O of 1. In other words, big O of n.
Did everyone get that?
Here's another sequence. First, again,
Really quick, so that one was saying that we're going to have to go through that for loop n times. So even though what's inside of it is big O of 1 or constant time, because we have to go through it however many times n is, then it's theoretically big O of n. So it keeps going until it's done there.
n is big O of 1, and if O of n. The total time is the summation of these two, but remember we drop low order terms. When n gets large, the time it takes to compute y is meaningless. For loop dominates the runtime. Finally, let's look at quadratic time. I think you can see that the print statement will be executed n times n, which gives us big O of n squared.
And that's because it's going through the whole thing
Let's do 2 more
up until
examples,
n twice
covering
here.
everything we've talked about. Say we have the following block of code. What is its total runtime? Well, we know the runtime for each of these, so the total runtime is simply the max of the 3. The nested for loop dominates here, so we get big O of n squared. How about this if-else statement? Pretend the sequence of statements in each clause have already been deduced to the big O's shown. We talked earlier that when we're discussing big O, we usually look at worst case scenario. So for this situation, we choose the largest runtime. Happens to be big O. I hope this gives you an understanding of big O notation. Let's wrap up by talking about the real world. When you're coding your algorithm, please realize that constants absolutely do matter. A lot of situations have small input sizes, so a constant of 2 or 3 could have a large impact. Last, in reason, be cognizant, average case. Depending on your application, this may be more applicable for your algorithm. As always, thank you for watching. Please subscribe if this helped you.
Okay. So big O notation is basically we're trying to figure out, how efficient, like I said, how efficient this algorithm is. So Big O cheat sheet's really awesome. It has that the complexity chart that shows kind of the range of what's good and what's bad. Like if you're up here, your algorithm's probably pretty slow. That's not great. I mean, like if you don't have very much stuff, it's kind of whatever. But if you're dealing with a lot of data, you don't want to be dealing with that. Some common data structures. So we can see like let's look at an array. We said that this is for accessing. So if we had an array right here, and I said, okay, I want an element at position 2, it gives it to me immediately. It doesn't have to iterate through it all. But if we look at like our stack, remember that we had to go through each element in the stack in order to get to a particular one. So that's why we say that it's big O of n, because you could possibly have to go through every single thing in the stack just to find one element. On the other hand, some of these are even better. So like a stack has better insertion deletion. Why? You're only dealing with the top thing. You already know where that is. So you're saying, oh, put something on top, put something on top, or take that thing off. So that's why, different data structures are going to have different complexities for different operations that you have on them. There's also array sorting algorithms that are going to be more efficient or less efficient, and sometimes you have to do something less efficient because of the way that you need to sort it. That's okay, and you should know that is going to be an issue. Other than that, though, does anyone have any questions about Big O? I don't want to throw too much at you right now.
Sorry, I'm asking a lot of questions, but during the video, they're comparing the algorithms, and were those the worst cases that they're looking at? Or
Yeah. So I mean, so that would be worst case, because I mean, best case is something like your so like their n squared ones, where they had 2 for loops. They had one for loop inside of another for loop. I mean, ideally it would be it's the very first thing that if you're like searching for something, it's the very first thing that you're searching for. And then that would be like best case, right? Worst case, you have to go all the way through everything in the array. And so I think they have like print X and Y or something like that. So that's actually a really good example of they are going through every single thing, because it's not like they're searching, they're just going through everything. So they were looking at worst case there. But yeah. Anyway, I have resources up that you can all go. These are just things that I found. There's a cool Udemy course. There's some other free Code Camp has some cool stuff on there for data structure and things like that. Also, I put up some good links for interview prep. HackerRank is awesome, and so is LeetCode. They're kind of the same thing, where they give you problems and they kind of rate them as easy, medium, hard, whatever. You can do it in different languages. You can do whatever.
So I've been on HackerRank before, and some of those like medium and hard ones are like really killer. But in some interviews, they kind of like a lot of companies focus on the easier ones, and a lot of companies focus on hard ones too. So
Yeah.
like what have you found to be most useful?
I think so. When I prep for an interview, I go through HackerRank a ton, not because I think that they're necessarily going to have the question there, but getting myself in the mindset of like, I'm thinking, what's going to be the most efficient thing for me to do in this kind of situation, what data structure might be useful. So just doing them is really helpful to get in that mindset. I think that's...
So which ones do? You do like easy ones or the hard ones?
I kind of work up. So like if I'm like, okay, I'm going to work on this for like 2 hours or something like that, I'll be like, okay, do some easy ones first and then start doing medium and stuff like that, and hard. I don't think doing the hard ones are necessarily worth the time, because it's like if it's going to take you too long, then that's not worth it. I kind of like to distribute it. I've had interviews where it's like, 4 hours of interviews, and one of them asked about binary search trees, another one asked about linked lists, another one asked about arrays, and so it's like it's hard because you just kind of got to be prepared for everything. But I do like that these are just good places to go for those things. There's also this interview tech book, or tech interview handbook, which someone made it, and it's just like this awesome like, here's something on the coding round, here's behavioral round, here's all your algorithms that you should make sure to know and everything. So I think going over that, being really solid with your with what you're doing and just everything is really important. Yeah. Anyone have any questions? If not, I think we're good. Thanks for coming. I hope this was helpful and